Alright, what is up my homies? Welcome to Brainmelt University. Today we're going to be talking about spanning tree protocol. This is a protocol that is extremely necessary in modern network and is extremely dense as far as how much theory is involved, but today we're just going to be giving a broad overview about what spanning tree is, what it does, and why we use it. As always, if you have any questions, feel free to drop them in the comments below, and please like, subscribe, and share with your friends so that we can help out the YouTube algorithm and keep us on the air. With all that said, let's get started. One of the biggest problems we have to overcome in modern networks is creating redundancy to help take over if a particular device or link fails without creating loops in our network. A network loop is where traffic can just travel around in a circle endlessly. Layer 3 of the OSI model, the network layer, does have the ability to detect network loops and prevent traffic from just roaming around the internet indefinitely. IP version 4 calls this mechanism time to live. IP version 6 calls this mechanism hop count. If that particular packet goes through too many routers, it will just get thrown away because the routers involved just think that this packet is never actually going to get to its destination network. However, if we're talking about traffic that's never designed to leave a particular network, this creates a lot more trouble. Traffic that never leaves a network is never going to actually jump from one router to another, and so therefore that time to live or hop count is completely useless to us for preventing what's called a broadcast storm. What a broadcast storm is if you have a number of switches all rigged up in a circle, if one device sends a broadcast message, a broadcast is just a message sent to anyone on an entire network, then that broadcast message is just going to be passed from switch to switch to switch, and it's never going to end because by the time it gets to the end of the chain, that last switch just passes it right back to the first one that got it. This is called a broadcast storm. Eventually, you can have so many broadcasts just traveling around in a circle that your switches cannot process the sheer amount of traffic, and they will actually end up either crashing, throwing away legitimate traffic, or you're going to end up with other issues altogether. This is why we created something called spanning tree protocol. Spanning tree protocol is a protocol designed to prevent switch loops from existing. What spanning tree does is it looks at how many switches are connected to each other, and if it detects that two switches are connected to each other in more than one way, it will actually disable what it views as the less efficient of these two connections. The way that spanning tree works is it elects what's called a root bridge. A root bridge is a symbolic center of your network. Root bridge election is based off of three things. It's based off of, number one, a priority value. A priority value is a 16-bit value, meaning it could range from anywhere from 0 to 65,535, but specific to spanning tree, it can only be incremented or decremented in increments of 4,096. This makes it a little bit easier to not have to memorize so many different priority values, but it also kind of makes it a pain to have to count by increments of 4,096. The second part of a root bridge ID is the VLAN identifier. So there's also 4,096 individual VLANs, excluding VLAN 0 and 4,095. So with the 4,094 VLAN IDs that remain, this is added to your priority value. So if we're on VLAN 1 and we're using the default value, which is smack dab in the middle, of 32,768, 32,768 plus 1 equals a root ID of 32,769. The final component of a bridge ID is the MAC address of the device itself. So one of the major problems with spanning tree protocol is that if you do not have any custom priority values set and all of your devices are on the same VLAN, then they're going to elect whoever the root bridge is based off the lowest MAC address. So since your MAC address is basically a serial number assigned by the manufacturer, that means that your oldest switch in your entire network is what's going to become the symbolic center. That might not necessarily be the best case. You're going to want your most powerful switches to be that symbolic center. So when it comes time to elect a root bridge ID, you're going to want to set custom priority values on your network. You also have the option to just specify who you want to be a primary and secondary and ignore the bridge identifier whenever you're doing your elections. So that's a lot of theory behind it, but let's go ahead and talk about the individual spanning tree protocols themselves. So spanning tree protocol has been around for a very long time, and when it first came out in the 1990s, it was pretty game-changing. Spanning tree protocol has not aged well. One of the problems with spanning tree protocol is while it is doing its spanning tree algorithm calculations, your device is not actually forwarding traffic. So you'll notice on a lot of switches when you connect another switch to it, it takes several seconds for that light to change from amber to green. This is actually the spanning tree process of trying to make sure that you haven't just established some sort of switch loop in your network. While it's doing those spanning tree calculations, then no one is actually passing traffic. This can cause quite a bit of downtime if you have an unstable network segment somewhere where your switch is constantly power cycling or you're having some sort of other issue involved. This can mean that you have a lot of wasted man hours while all of the employees temporarily lose their network connections. This can also mean a huge headache for your IT department, as they are constantly being flooded by complaints of people saying that the network is down, and by the time the network technician goes to troubleshoot, it's already come back up because spanning tree has finished its job. Spanning tree, for all of its faults, was really nice, and one of the major components that makes spanning tree nice is that it's actually an IEEE standard. This means that spanning tree protocol is universal and can be used by virtually everyone. IEEE specified spanning tree protocol in standard 802.1d. There is another problem with spanning tree besides just how long it takes to converge your network. Another major problem with spanning tree is that it is a global process. Spanning tree does not recognize that there are unique VLANs in a switch that may not be actually communicating with each other. So if you have 4 switches connected in a loop, but 3 of them are communicating on VLAN 1 and 3 of them are communicating on VLAN 2, and these 2 are opposite to each other and slightly overlapping, now you have this issue where there actually is no switch loop in place, but spanning tree still sees 4 switches and it's going to disable one of the links, basically killing the connection for one of these 2 VLANs. This is a huge problem, and that's why Cisco created a proprietary version of spanning tree based on the original 802.1d protocol, and it calls this per VLAN spanning tree, PVST+. PVST+ does exactly what its name implies. It runs a separate instance of spanning tree on every single VLAN. Now, this is great if you own all Cisco switches, but it's pretty terrible if you have a mixed vendor environment or you just don't purchase Cisco equipment. This is why a new version of spanning tree had to be created that is capable of doing similar things to PVST+ without infringing on Cisco's copyrights. That's why an open standard called 802.1s was established. This is the multiple spanning tree protocol, or MST. It might also be referred to as MSTP depending on whose textbook you get, whatever. MST is a great alternative to per VLAN spanning tree, and in some instances can actually be better. For instance, it allows you to group multiple VLANs into a single instance. So say for instance your organization has 3 different units, and each of those 3 units has their own network, but they also have their own IP phone network. Now you can actually group their data and IP phones together in a single instance, because these 2 networks should overlap the entire time anyway. This means that instead of having to run 6 instances of multiple spanning tree, you can actually get away with running 3. This does come in handy because multiple spanning tree does have a major drawback in that it can only support up to 15 instances at once. So if you're dealing with an extremely large network that has dozens or even hundreds of VLANs, you're going to have to group several together anyway. This is also less resource intensive than per VLAN spanning tree, where if you have hundreds of VLANs running and you have hundreds of instances of per VLAN spanning tree running as a result, that can really bog down your device's system resources as they're constantly having to do recalculations and make sure no one's added anything to the network. 802.1d, because of its slow convergence, did need a pretty major overhaul, and so in 2004, 802.1d was upgraded using a new version of spanning tree called Rapid Spanning Tree, RSTP. RSTP is defined by the IEEE standard 802.1W. 802.1W does two major things. 802.1W is a lot better at calculating the efficiency of a network link because it was designed with higher bandwidth links in mind. The original 802.1D standard never really took into account that we might be seeing networks that are 10, 40, or 100 gigabits per second in speed. After you get into speeds that are faster than 1 gigabit in length, you end up seeing a lot of problems with exactly how fast that link really is if you're using the plain old spanning tree protocol. That's why 802.1W is so much better for modern networks, because it is capable of recognizing and understanding higher bandwidth and calculating cost accordingly. 802.1W also increases the speed of network convergence by eliminating unnecessary steps when it comes to calculating convergence and making sure that no redundant loops have been created. But 802.1W has the same basic limitation as 802.1D, and that is it runs as a global process. It is incapable of recognizing the difference between individual VLANs running on a switch. That's why immediately after 802.1W came out, Cisco managed to get away with updating its per VLAN spanning tree protocol, basing this new protocol on the new 802.1W standard. This allowed Cisco to create the Rapid Per VLAN Spanning Tree Protocol, or RPVST+. RPVST+ is exactly how it sounds, exactly like per VLAN spanning tree, but based on 802.1W instead of 802.1D. The multiple spanning tree protocol was also updated, but they didn't change the 802.1S designation. They didn't come up with a whole new protocol, they just updated it to support the newer version of 802.1W. When we're talking about the spanning tree protocol, we have to recognize how each of these protocols ticks. That means that even though 802.1D is pretty ancient and we shouldn't really be using it in modern networks, you might still be called upon to work on an outdated network, and so you have to be able to understand that these protocols are probably going to be functioning the way they're intended, which is probably not the way that you want. That's why we need to talk about port states. As you connect one switch to another, that interface is going to go through a number of states as spanning tree is attempting to calculate whether a organization has created a loop or not. The first state is the blocking state, and this is pretty self-explanatory. This means that spanning tree protocol is blocking all traffic other than spanning tree traffic. That means that you're not actually forwarding anything from one to the other. This is where you look at a switch, and as soon as you plug it in, that link light on that interface turns amber instead of green. This is because spanning tree is just starting to do its job, but while it's doing its job, it's still going to block traffic to make sure that it's not wasting anybody's time. From there, we go to the listening state. The listening state is basically 15 seconds of dead air. The listening state is where it's just sitting there waiting for what's called a bridge protocol data unit, which is the particular data units that spanning tree exchanges from switch to switch, and it's waiting to see if another switch has been connected. This listening state is 15 seconds whether it receives a BPDU or not. This means that you're going to spend a minimum of 15 seconds doing absolutely nothing while spanning tree just goes through listen. Next, we go through the learning state, and this is where BPDUs are actually exchanged. After all of these adjacencies have been formed, they've discovered who the actual root bridge is, and they've determined whether loops have been created. The device makes the decision to move either into the forwarding state, which is where it's actually passing traffic besides just BPDUs, or it goes back into the blocking state. In addition, we also have a disabled state, and disabled basically just means the port is not functional. When we moved to rapid spanning tree, we actually did a little bit of a revamp. Instead, there's only 3 port states when it comes to rapid spanning tree. You have forwarding, you have discarding, which is the rapid spanning tree equivalent of blocking, and you have learning. So we're avoiding that 15 seconds of dead air and moving directly into the exchanging of BPDUs. Rapid spanning tree takes virtually half the time, if not less, depending on how new your switches are, in order to calculate these redundant links and disable the least efficient ones. And lastly, we need to discuss the types of ports in a spanning tree network. Spanning tree provides certain designations to ports depending on how they function. Depending on whether you're talking about rapid spanning tree or plain old spanning tree, you're going to have a number of different terminology. Multiple spanning tree and your per VLAN spanning trees will use the same terminologies depending on whether you're using the versions based on 802.1d or the versions based on 802.1w. When we're talking about 802.1d, there are three major port types you need to concern yourself with. The first type of port is called a designated port. A designated port is any interface that is forwarding traffic but is not directly downstream to a root bridge. This gives you a little bit of a shortcut to figure out just who the root bridge in your network is. If you're looking at a switch and it has nothing but designated ports, that's a pretty good tip-off that that device is the root bridge, because you can't have what's called a root port, which is an interface directly downstream to a root bridge, if you are the bridge. You could also end up with a blocking port. A blocking port is any interface that's been determined to be redundant and is not the most efficient link back to the root bridge. This blocking port is placed into the blocking state, so you can kind of keep those two together. With rapid spanning tree, we decided to go with an alternate port. An alternate port is any port that is kept in an alternate state, meaning that if that root port does go down, the alternate port is moved from a discarding state and into the forwarding state so it can still get back to the root bridge. This makes rapid spanning tree nice for recalculating these, and it kind of shows that the alternate port is not permanently disabled, it's just temporarily done so to prevent broadcast storms from occurring. Otherwise, your rapid spanning tree uses the same terminology, with root ports, designated ports, and your blocking port has just been renamed alternate to reflect the fact that it's not disabled, it is simply not being used at the moment. And with that said, that's spanning tree protocol. That's a lot of information to throw at you, and this discussion gets a lot more in depth than just this, but this should give you the basics enough to be able to understand what spanning tree protocol is, what the different versions are, and why you would want to use different versions depending on whether you're using an all Cisco environment or a mixed vendor or non-Cisco environment, as well as the advantages of using something like MST versus 802.1w or 802.1d. If you have any questions, please drop them in the comments below. And once again, please feel free to like, subscribe, and share with your friends so that we can make the world a more connected place. Thanks so much, and we'll see you here next time at Brainmelt University.